back to the session, right. In today's session, we will discuss about the state variable analysis, right. So, we will see in detail what is state space model, why we need the state space model, and what are the basic importance of state space model as compared to our previous model that we had seen to model the control system. Okay. So, basically our control system can be modeled via transfer function, via differential equation, and the third method is here state variable method. Okay. So, we will see first why we need this space model, right. Then we will see the mathematical representation of state space model, basically it will be the introduction. Okay. Then we will discuss the state space model with certain example. Then we will see the basic terminology used in the state space model. Okay. So, why state space model is needed? So, that is why we are discussing here the advantage and limitation of the transfer function model that we used in the previous unit. Okay. So, now you can see here the benefits. The one transfer function are defined, you can say, in Laplace domain. It means whenever we have to study the system in frequency domain, we are referring the Laplace transform method, that is transfer function method. Okay. So, in the transfer function we are observing what? We are observing our output in S domain and our input in S domain, and their ratio would be the transfer function. So, in the transfer function case, what is happening? We are not initializing the state. Okay. It means the initial value of the system is 0 in case of transfer function. So, this is the assumption that we have to use in the transfer function, right. So, it means if I am dealing with any control system where it is having certain initial state, just like a electrical network, if it is having a certain capacitance and inductance, if they are storing certain energy, then those initial values will not be considered in the transfer function. Okay. So, this is the one point. And system you can say here the input view and output view, we can see in terms of frequency, we can estimate the bandwidth from transfer function model, and you can say it is very dominant in the industry, right. So, as I told you, this transfer function is only valid for linear system. So, whenever my control system behaving in a non-linear way, then transfer function will not give us the correct model. So, in that case we have to look for the alternate approach. Okay. So, transfer function can be extended to non-linear. In a exceptional case, we have to apply a lot of complex model or complexity in terms of equation, then we can go for modeling of non-linear system using transfer function. Okay. And the transfer function is limited to the SISO system, that is single input or single output system. Whenever multiple inputs present in the system, then transfer function will not give us the correct state or correct modeling. Okay. So, whenever we need the MIMO system, it means multiple input and multiple output system modeling. In that case, we have to refer the state space model, right. So, MIMO system, you know very well, nowadays in the communication, we have to set a lot of antenna in our area, so that a multiple mobile user can receive the signal. So, we have to use array of antenna that will make a MIMO, that is multiple input and multiple output system. So, those system can't be modeled using transfer function, we have to look for the alternate solution. Okay. And whenever I am designing any transfer any model or any control system, then I can't observe its internal behavior and the internal variables which will affect the output of the system. Okay. For that purpose, we have to look for alternate solution that can look the dynamics involved inside the control system to observe the output. So, these are the basic limitation of transfer function, right. So, that is why we need a solution which can explore all this problem and give us a finite model. Okay. So, that is why we are going for state space model. So, generally I am taking example of this model. So, I am considering this model as a chemical process plant. It can be used in the petrochemical and oil industries. So, here suppose this is a chamber where we have to maintain certain volume of steam, where we have to maintain certain temperature of the steam, and then we have to maintain certain pressure over the steam inside this boiler. Okay. And we have to define certain subsystems. So, we need to add here certain system which will monitor the pressure, which will monitor the temperature, and which will monitor the volume of the you can say steam that we are providing in this boiler, right. So, all this sensor or all this system we need to define in this system. Okay. So, whatever changes, suppose my volume of steam is varying with respect to time, suppose this volume is changing with respect to the state of the other chemicals or other material, right. So, we can observe that these factor going to affect my output, how they are changing my output, how they are varying with time, all these analysis we can observe in the state space model. Okay. So, basically the variable which is affecting my output and these variable is changes by providing the input, they are known as the state variable. And whenever I am modeling using the transfer function, then I do not know what is present in this box. I have to consider only on the input quantity and I have to observe what is coming at the output, what is running inside the system I do not know. So, this is the statement of transfer function model, right. So, whenever I have to look inside the system, we have to go for the state space model. Okay. So, now we will see here the state space model, right. So, the state space model basically consists of the three element, one is the input, output and you can see the internal variable of the system, and this internal variable of the system is called states. So, state space method came to existence in the era of 1960. So, the state space model generally considered in modern control theory, and if we talk about the control theory before 1960, so in that case we used to deal with the transfer function, right. It means our frequency domain analysis, which will include the Bode plot and which will include the Nyquist plot, polar plot analysis, all those analysis are still today they are very famous. Okay. So, they are used with the help of, or they are designing or they are implementing with the help of transfer function only. So, after 1960 whatever modeling we are doing in the industries with the help of state space model. Okay. So, this is the basic introduction, and with the help of state space model we can predict the present state, past state and future state of the system, okay, which is not possible with the transfer function. So, in the state space model if we see, so it is the representation of dynamics as I told you. Okay. These dynamics are the state variable of the system in terms of n set of differential equation. Okay. So, the dynamics governed by the system, it will explain by the differential equation used to model the control system. Okay. It converts the nth order differential equation which governs the dynamics into n first order differential equation. Okay. It means the linear way, in the linear way we can analyze our system using the state space model. So, it will simplify the complex differential equation into linear differential equation, and the number of state basically given by the order of differential equation. Okay. Suppose if the differential equation maximum order is d 2 y over dt square plus dy by dt, this is the equation, right, equal to 2 y plus 3. So, here the highest order is 2. So, I will say the 2 state variable we have to define in our model. Okay. So, our order of differential equation gave us the number of state variable that we are going to use in our system. Okay. So, now this is example of an electrical network, and generally the state variable in terms of electrical network, they are given by the energy storing element. The number of energy storing element is equal to the number of state variable in terms of electrical network. So, here we can see one is the inductor, second is the capacitor which can store the energy, right. So, on the basis of it I can say one state variable will come from inductor in terms of current, second state variable voltage will come in terms of capacitor. So, these two storing element will give us the 2 state variable. Okay. So, whenever in the exam it is asking how many state variable possible in the system, you have to note down the number of energy storing element just like inductor and capacitor, and you will get your answer, that is 2, right. So, in this modeling what I need to do, whenever I have to write the state space model of this network, I have to convert this model into differential equation, and from those differential equation I will obtain my state space model in terms of matrix. So, how it is? So, we will see in next slide. I will apply KVL in the system and then I will choose here two output, one output across R, second output across C in terms of voltage V R and voltage V C. So, I am saying it is y 1 t one output, y 2 t as second output. Okay. So, one equation, if we apply KVL, this is the equation V I equal to L D by dt plus R I t plus V C, this is the second. Okay. So, these two equations shows the KVL of the previous circuit diagram, and if we separate out this differential variable, that is dVc over dt in the LHS and remaining term in the RHS, then what will happen? So, this term you can see I am using this equation. So, here dVc by dt is given by this term. Now, this equation I am using here by separating out di by dt and I am getting this expression. Okay. So, here you can see the differential term coming in the LHS, remaining variable coming in the RHS. So, I told you the state variable coming from inductor and capacitor in terms of current and voltage. So, V c voltage is my one state variable, I t current is my second state variable. Okay. So, if I want to represent this equation in terms of matrix, so this is the differential matrix dVc over dt, di over dt, and this coefficient will come. So, when I write this equation, so here V c term is absent, so I can write 0 times of V c is here, right. So, here one my coefficient is V c, second is I t, V c coefficient is 0. So, I will write here 0 first, then I t coefficient is 1 by c, I will put here 1 by c. So, this is the conversion of my equation 1 in the matrix of first row. Okay. In the same way, when we go for equation number 2, di over dt given by this term, I t and V c, both variables are present here. So, V c and I t, the coefficient of V c is minus 1 over L. So, I will put here minus 1 over L. Coefficient of I t, you can see it is minus R over L. So, I will put here minus R over L. Okay. And this one is the input. So, we will write separately. So, plus I will make a separate matrix of V I t. So, V I t is absent in equation number 1. So, I am writing here plus 0 times of V I of t, it is the input. Okay. So, here I will write 0 in the first row because it is 0 in first equation. In the second equation, the coefficient is 1 by L, I am writing this. So, this is the matrix representation of this given equation. Okay. Now, I have to assume here my state variable V c as my first state variable x 1, I t as second state variable x 2. Okay. And I am assuming that u is the variable which is representing the input quantity. Okay. So, here what I can say, if I replace x 1 by V c in the above equation, so this equation can be written as dx 1 over dt equal to this much, dx 2 over dt is written this much, and this change will come in the matrix and this change will come in this matrix, and this equation will make the state space model of the system, right. So, this is a basic idea how to model a state equation from a electrical network, right. It means we need to obtain the differential equation and then we need to model them in terms of matrix and we will get here the state equations, right. Now, in the same way we would like to observe my output. So, I had shown you in the previous slide that we are observing output across R. So, one y 1 t is here, we are observing output across C, second is y 2 t here. So, I will write equation for it. So, for output equation y 1 t written is like this, y t equal to V c, y 2 t equal to V r, and V c is given as x 1, right, because we assumed in the previous slide you can see we assume that V c is given by x 1, okay, and input is not present. So, I am saying 0 times of u is the input variable, y 2 t is V r, V equal to I r, I t is the state variable, it is x 2 I assume in the previous case. So, r times of x 2 plus you can say 0 times of u, because input is not present in this equation. Now, I have to model it in terms of matrix. So, 1 I will make y 1 y 2. Now, state variable is here x 1 and x 2. So, in equation 1 only x 1 is present, x 2 is absent. So, I can make 0 times of x 2. The coefficient of x 1 is here 1. So, I will writing here 1. Coefficient of x 2 is 0. I will write here 0. In the same way, second equation I am getting r x 2. So, I can write here plus 0 times of x 1. It means x 1 is here absent. So, I can make 0 coefficient for x 1 and r coefficient for x 2. So, this is my output state equation. Okay. So, this is the basic of the state space model. It means it consists of two equation. This is the state equation that you are observing here, and second is the output equation. So, state and output equation combined together to gives you the state space model, right. So, here if I observe my matrix, that is this term dx 1 dt. So, I am assuming this differential term in terms of x 1 dot. So, dx 1 over dt can be written as x 1 dot, dx 2 over dt can be written as x 2 dot. Okay. So, they are the differential state variable. So, x dot basically gives you this term, it means dv by dt can be written as dx 1 over dt and di over dt can be written as dx 2 over dt, and this is known as differential state vector. X we know very well, v and it, x 1 and x 2 they are the state vector. A matrix, this will give us the state matrix. Okay. In the same way, when we analyze our output matrix, so here B will this is from the state matrix, B is acting as input matrix, okay, and C is here output matrix. So, how this input and output is coming, we need to look in the previous equation. So, here I am making this matrix as A state matrix, this matrix corresponding to the input I am saying this is B input matrix, and whenever I am observing my output, this matrix is regarding output variable. So, this is the C matrix which is explaining the output variable, okay, and this term is coming B for input, C for output, and D is here direct transmission matrix. In some textbook we are saying it is coupling matrix also. So, what it means we will see later. Okay. And if we see u is the scalar input, y is here the scalar output, and the generalized equation would be x dot a x plus b u, y equal to c x plus d u if you observe the previous matrix. Okay. So, this matrix is x dot, and you can say this matrix is A, this matrix is x, and this matrix is B, this matrix is u A x plus b u, okay, and this matrix is written as y equal to, this is C, this is x, this is D, and this is u. So, D matrix is 0 here. I told you later about this D matrix. Okay. So, this is the basic equation that we are using to represent the state space model, right. So, this is my state space model in this two equation. This is known as state equation, and the bottom one known as output equation, which will help us to do the analysis of control system. Okay. So, the basic terminology that we have using here, one is state. So, it refers to the smallest set of variable whose knowledge at t equal to t naught together with knowledge of input at t greater than or equal to t naught gives the complete knowledge of the behavior of the system at any time t greater than t naught, right. So, here we need to select the minimum set of variable, right. For example, what I need whenever I am designing my space system, I want to launch the satellite. Okay. So, what I am doing initially, I measure the mass of satellite, it is m0 on earth station. Now, on the rocket I launched it, it goes to the distance of 10 kilometer, it will consume certain fuel, mass will change to m1 because mass is decreasing because my fuel is going consumed. Okay. So, that is why my next mass is m1, and after distance of 1000 kilometer, the mass of satellite would be m2. Certain stage in the satellite they will separate out, and I will get reduced mass of the system, that is m2, and whenever finally I reach the orbit, again finally I will get a very small satellite with a very small mass of m3. So, what is happening here? My mass m1 change with time, mass m2 changes with time, mass m3 this is change with time. This is the time varying system, right. So, what is happening? I must know what is the state at t equal to t naught, that is state of the mass of satellite at earth station, and when it reaches the orbit for t greater than t naught, how my mass is varying. This thing can be explained by the state of the system, right. So, this process can't be explained by transfer function. Okay. So, that is why we are not using transfer function model to model a time varying system, right. Now, state variable, so they are the smallest set of variable, right. The smallest set of variable means the variable which will defines the output, and if you apply any input it will change and reflects the output. So, only we need to consider those state variable, right. For example, if I have to make a tea, so what is my input? Input is my milk and tea leaves, right. We are providing input, and what is the output? Output is my tea. In between I am using the cardamom, I am using ginger for my flavor. Okay. So, these all also variable to obtain the tea, right, but my important variables are milk and tea leaves. I can avoid the cardamom and ginger according to my flavor, they are not required, they are optional. Okay. So, here these two variable are the minimum set of variable which can obtain t at the output. So, for state variable we have to select only important and minimum set of variable which will explain the system. Okay. So, this is the requirement of state variable, and if we combine those state variable it will become state vector. Okay. So, now we will see here the state space equation. So, we are concerned here with the three types of variable that are involved in the modeling of dynamic system. One is the input, output and state. So, all this thing we had seen in the previous slide. If we are having the n number of input, we will write u1, u2, ur. If we are having the n number of output, we are writing y1, y2, y3. So, this is the generalized representation of the state space model of a MIMO system, which is having the n number of input and which is having the p number of output. Okay. In between, which is governing this conversion or which is controlling this conversion or controlling this system is given by the state variable. So, this state variable decides this number of output. Okay. So, this is the generalized modeling of state space model. Now, if we see, this is the equation that we define, this is the state equation and this is my output equation. Okay. So, x t is the state variable, right, which is given by this vector x 1, x 2, x n. So, its order is n cross 1. So, here n depends on number of state variable. If I am having thus one state variable, order is 1 cross 1. If I am having two state variable, order is 2 cross 1. If I am having 3 state variable, order is 3 cross 1. So, n is the number of state variable I am using, and that will decide the size of this matrix. X dot is the derivative of state variable matrix. A is the system matrix given by this order of n cross n. Again same concept, 2 state 2 variable, 2 cross 2, 3 variable, 3 cross 3. So, what system matrix shows us how the various state variables connected to each other inside the system is given by this matrix. Input matrix will tells you how the input vectors or these input variable affecting or changes the state variable given by this input matrix. Output matrix will tells you how the changes on the state variable reflecting on the output state is given by this output matrix. And feed forward, whenever I have to bypass the system or skip the system from the, you can say, to process the input, I have to go for the D matrix, this is feed forward matrix. You can see this concept would be clear here. So, here this is my input t u t and it bypasses the system and reaching to the output. It means what I am doing, I am bypass this input to bypass, or you can say to surpass, or to not cover, to I am not allowing this input to go through it. I am providing a alternate way or feed forward path to this input to reach to the output state y t. Okay. So, this is the feed forward example, that is D matrix. Okay. So, here in this matrix, n is the number of state variable which will decide the order of this matrix, m is number of input variable, p is number of output variable. Okay. So, this is the generalized equation that we discuss in the next session. Okay. So, thank you for today. This is the basic introduction to the state variable. Remaining theory of state variable in depth we will see in next session. Okay. So, thank you for today.